our friends at UGM for organising this fascinating meeting, and I'm delighted to introduce three terrific speakers. We'll hear from, firstly, Duane Gubler, and Raman Velayudan, and then to finish, Henrik Salje. So three fabulous speakers to tell us about why dengue continues to be a global health threat and what's on the horizon in terms of tools to control dengue in all of the parts of the world where it's a problem. So we have three recorded presentations, and I'll introduce each speaker one by one. Our first speaker is Duane Gubler, who many of you will know from many decades of distinguished work and leadership in the field of arbovirology and vector control. Duane is an emeritus professor at the Duke NUS program in Singapore, and prior to that, really a long history with CDC in both the US and in Puerto Rico, operationally battling the problem of dengue and other Aedes-borne diseases. So, and Duane will set the scene. Why has dengue been such a big problem? So if we could roll to the first presentation, please.
Well, first of all, let me just say what a great pleasure it is for me to participate in this important meeting, and in Jakarta, and in collaboration with Gajah Mada University. It's one of my favorite places, and Indonesia is one of my favorite countries. But we're talking about a very important topic this morning. I've been asked to talk about why haven't we defeated dengue after all of these years. Next slide, please. In the way of background, I'd just like to remind you that over the past 70 years, we've seen a dramatic emergence of epidemic dengue and other Aedes transmitted viral diseases. It began in the 1970s with the advent of modern air transportation, accelerated in the 1980s and the 90s. We've gone from having a few hundred to a few thousand cases of dengue in the 1950s and 60s to the present decade, where we have 3+ million cases of dengue every year. Next slide, please. It's why have we seen such a dramatic increase in disease is complicated, but it's basically associated with several global trends that are the principal drivers of this emergence. The global trends of population and economic growth that led to urbanization and globalization and modern transportation have been the principal drivers. These have led to increased movement of people, animals, and commodities, which in turn have increased urban populations of susceptible hosts. We now have urban populations of megacities of 10 to 20 million people. It also increased the spread of the mosquitoes around the world, and in both in these urban and increased movement of the viruses. Most of these urban areas have not had effective surveillance programs, nor have they had effective mosquito control programs. And all of this has led to increased dengue transmission and other Aedes transmitted viral diseases in the urban centers of the tropics and the subtropics. And this has led to increased epidemic dengue and Aedes transmitted diseases. And next slide, please. It's not just dengue. It's, as I've indicated, other Aedes transmitted viral diseases, primarily chikungunya and Zika, as you can see here. But next slide, please. but there are other arboviruses that are at high risk as well. All of these viruses can be transmitted experimentally by Aedes aegypti, but the main disease that we're worried about is yellow fever, which is high risk for breaking out and causing major epidemics and spreading into the Asia Pacific region. Next slide, please. So just to remind you that we have been successful in the past in controlling these diseases, beginning in 1900 with the yellow fever transmission in Cuba, but many successful programs. I'll talk about why those were successful in just a moment. Next slide, please. And this continued after we had DDT available with the 1950s and 60s hemispheric Aedes aegypti eradication program. We eliminated Aedes aegypti from 22 American countries. And this prevented epidemic dengue for the better part, and yellow fever for the better part of 50 years. The 1950s and 60s global malaria eradication program was also successful in controlling malaria in many parts of Asia, the Americas, and some parts in Africa. More recently, two programs, the Aedes aegypti control program, dengue control program in Singapore, controlled epidemic dengue for the better part of 15 years, and the Cuban dengue control program prevented epidemic dengue for the better part of 16 years. Both of these programs have subsequently failed, but for a variety of reasons that we won't go into right now. So we have had success in the past in controlling these diseases. The reason, next slide, please. The reason for these successes are complicated, but I've listed most of the major points here. I'll run through them very quickly. But most of these successful programs were top-down paramilitary type of programs that had put a lot of emphasis on detailed mapping of larval habitats. They tremendous dedicated attention to details and a dedicated and well-trained staff to implement the programs. These were critical. Most of the governments during this period in the 50s and 60s were autocratic governments, but they were very supportive of disease control programs like dengue. They implemented fines for allowing mosquito to breed on your property. The cities were much smaller. Most cities were less than 1 million population, or around 1 million population at that time. There were not very many automobiles, and therefore not very many tires to spread the mosquitoes around the world. Airplane travel was minimal in those years. There were no plastics or few non-disposable containers to serve as mosquito breeding sites. And we had basically cooperative human populations. There was adequate funding, and most of the programs were regional, not just a single country, and they had a good residual insecticide in the form of DDT. Next slide, please. Beginning in the 1960s and 70s, however, there were a number of societal changes that led to a decreased success in these programs. In the 1962, Rachel Carson published a book called Silent Spring, which was the beginning of the environmental movement that we still see today. In the late 1960s, the war on infectious disease was declared won by infectious disease experts, and I'll come back to this in just a moment. This resulted in a redirection of infectious disease funding, and there were global policy changes in the early 1970s. They disbanded the Aedes aegypti and malaria eradication campaigns. They merged the all vector control programs under one roof, which spelled the death knell for Aedes aegypti because malaria was the most important program. And so most of the malariologists survived. The Aedes aegypti people did not. And they stopped using DDT, and we had no good residual insecticide to replace DDT. So all of these factors contributed to ultimate failure of our Aedes aegypti control programs. Next slide, please. So just to emphasize a little bit to what this war on infectious diseases being declared it basically resulted in complacency and apathy in the public and in public health officials and in policymakers, which then resulted in lack of political will and economic support, as I've already mentioned, deterioration in the public health infrastructure to deal with vector-borne diseases. There was a lack of technical expertise and trained personnel as a result of all of this, and the lack of community ownership and control program. People in communities where these diseases occurred were basically told that they had no responsibility. It was the government's responsibility. At the same time, the control programs became reactive control programs. The old proactive approach of trying to prevent epidemics disappeared. And the emphasis became on surveillance, not on control. There was dependent on passive surveillance, which is never very effective. The reactive control focused on using what we call ultra low volume or thermal fogging from vehicles and aircraft to control the mosquitoes, and on perifocal treatment around homes of cases. All of these approaches were not successful. It was always too little, too late. And of course, I've already mentioned the coincident global trends that were driving the increased movement of viruses and mosquitoes around the world. Next slide, please. So a lot of reasons for failure. And all of the tools that the methods that we used during this time essentially failed. And I won't go through them, but everything that we did essentially failed for the past 40 or 50 years. Next slide, please. So there is light at the end of the tunnel because there are a lot of new prevention and control tools in the pipeline. And this includes new mosquito control tools, including residual insecticide, genetic and biological control, and a number of other approaches. It includes biomarkers for severe disease to prevent fatalities with dengue. It includes therapeutic antibodies, antiviral drugs, and vaccines. So we have going forward in the next several years a lot of new tools as well as the old tools that we can use to control these diseases. But I would urge you to remember that there is no single approach that is going to be successful. These tools are going to have to be used in conjunction with each other if we're going to be successful. Next slide, please. So this is what a integrated top-down, bottom-up program in the 21st century should look like. In my opinion, the program needs to be an integrated top-down, bottom-up type of program. It needs to have active laboratory-based early warning surveillance. This is laboratory-based. I emphasize that. The programs need to be proactive in their mosquito control programs, integrating multiple new and old technologies. There needs to be better environmental management in urban settings. We need to effectively use the vaccines that are going to be coming online in the next year or so. And we should improve our clinical diagnosis and management, including the use of new antivirals that will be coming online, the use of biomarkers for severe disease, and therapeutic antibodies. We need better effective emergency response programs because epidemics are not going to go away. We need urban design and development. We feel that the Singapore example is one that a model that can be followed by most countries. And I don't have time to go into that right now, but when they started their program in the late 60s, they were a very poor country. They had a GDP lower than most countries in the Southeast Asian region. And here we are decades later, they've effectively controlled Aedes aegypti. They haven't controlled epidemic dengue yet for a variety of reasons that I won't go into. But we desperately will need to have political and economic support for these programs. And if we're going to be successful long term, the programs need to be regional. Individual countries, as Singapore is another good example, will not be successful if it's an individual country. All of the countries in the region need to participate. Next slide, please. So this is in graphic form what I feel a successful integrated program will look like. There are three main approaches for control: vector control, vaccination, and improved surveillance. Integrated with better clinical management and use of therapeutics, and with integrated with community engagement, more community and involvement. Excuse me. And it's important to emphasize that these programs need to be targeted. Every country, a lot of communities within countries are different ecologically, epidemiologically, economically, culturally. And so no one single approach is going to fit all regions. So the programs have to be adapted to local conditions. And finally, we need to mobilize international resources, insectoral resources. It's very important to realize that this is not only a public health problem, but it's an economic problem for most countries. So we need to use these funds to rebuild public health capacity in these countries. We need to fund program implementation and fund research on future interventions. Next slide, please. So let me just finish up by reminding you that this is not a new approach. In 1988, I was invited to give the Charles Franklin Craig lecture at the American Society of Tropical Medicine and Hygiene. This is one of their premier lectures, and they wanted me to talk about a program I had developed in Puerto Rico in the 1980s. This was published in the American Journal of Tropical Medicine in 1989 under the title of Aedes aegypti and Aedes aegypti-borne disease control in the 1990s, top down or bottom up. And I won't read this whole segment here, but it was the last paragraph. This is the last paragraph of this paper I wrote. And I just want to read two sentences here. It is my opinion, therefore, that neither top-down nor bottom-up approach alone is ideal for controlling Aedes aegypti-borne diseases in the 1990s. What we urgently need today are integrated control strategies that utilize the best of both approaches in the initial phase, with more emphasis directed towards a community-based approach as the program progresses or matures. So 35 years ago, this we recommended what we're recommending today. And the question is in, say, 2050, are we going to look back at this and say, well, we still haven't accomplished this goal of prevention and control of these diseases? Next slide, please. But again, the good news is that there's now wider support for this type of an integrated approach. The Lancet has appointed a commission, and we've titled it Cities Without Aedes Transmitted Diseases. It's a global commission. Approximately 30 countries are involved or have representatives on the commission. And we have several goals. The ultimate goal, of course, is to achieve cities without Aedes transmitted viral diseases. Again, Singapore is the example, the model that we want to use here. But the two goals, there's short term to optimize current interventions, rapidly integrate new emerging interventions into the control program to prevent epidemic disease right now. But long term, what we want to do is change how cities are designed and managed to build out Aedes aegypti. So it makes it much more difficult for Aedes aegypti to breed in these cities. And to do this, as I've mentioned earlier, the programs need to be intersectoral and regional if we're going to success. So with that, I will stop. And unfortunately, I'm in the United States, so I can't take any questions. But thank you very much.
And thank you, Duane. As usual, a fabulous historical overview of where we've come from in the world of dengue and dengue control. It's now a pleasure to introduce Raman Velayudan from WHO. And again, Raman will be known to many people in the audience. Raman's had a long history in WHO, trained as a medical entomologist. Now really the dengue point person in Geneva for both vector control and disease control, and has been a driving force behind the global strategy for dengue control, published a number of years ago now, but also involved previously in guideline development and in imminent guideline refreshes. So really good to hear from Raman, and Raman's going to be talking about what's new in vector control. If we can roll to Raman's talk, please.
Thank you very much. Thank you very much for this opportunity. I really appreciate this, and it's indeed a pleasure to give this short talk to you. So my topic is basically on dengue vector control and what's new. So essentially, we need to just give a brief introduction before I go into the real talk. And the introductory part is, what is the challenge we are facing today? So for dengue vector control, the main challenge is the growing level of insecticide resistance, increase in global temperature, which is of course climate change, more extreme weather patterns, which is also linked to climate change. We are also causing significant land usage changes. So there is a lot of problems with the way we manage our land. There is also a growing increase in travel and trade. So all this facilitates more problems for dengue control. And then in addition to that, we have to remember there is also the behavioral part of it. We are facing resistance among communities. And by 2050, almost 70% of the world will be living in cities, or in other words, we are getting more urbanized. So these are the key points we need to remember. It is not that vector control is a failure, but that vector control faces growing challenges. And these are some of the major challenges. So what do we do in WHO? So we are talking of new tools. And as we talk of new tools, the World Health Organization, we are actually answerable to 194 member countries. So all these countries come to us and they do assemble once a year at the World Health Assembly, where they have every free time to really ask us, meet us, and discuss things with us. So what WHO has done is we have established an advisory group for evaluating new vector control tools. And there is a pathway for assessing the new tools and also for pre-qualifying products. I'll just briefly discuss that. So this is what we call the WHO pathway of vector control evaluation. So first of all, if you have a new tool for vector control, you are supposed to submit an application which comes to our pre-submission coordination committee. And what we do in this group is that we assess the application and see whether this is a new tool or is it an existing tool. Say, for example, we are talking about a product like a spraying on the wall, a residual spray. It is an old product. It has been used for malaria control. It has been used for leishmania control. It has been used in other controls. So basically, in that case, if that product is used for residual spray, then it goes to what we call the pre-qualification pathway, which is the top one. So what pre-qualification pathway does is, they know that this product is an old product, basically as an old intervention. And so we really assess the safety, efficacy, and quality of the product. So that is what the pre-qualification pathway does. But in case you have a new tool, say, for example, I'm sure you're going to discuss Wolbchia. There may be other tools like sterile insect technique and other traps. So in that case, we don't have any policy recommendation or any recommendation from WHO. It has not been proven to have an impact on the disease. So in that case, this tool or this intervention goes through a new intervention pathway. And here we have a committee called Vector Control Advisory Group. And this group helps in planning. This is VCAG, Vector Control Advisory Group. It also helps in assessing your trial design and also makes final recommendation on the product. So this is the role of Vector Control Advisory Group. It supports WHO to guide the applicant on study design and generating epidemiological data. It supports WHO to assess the public health value of any new tool. So what I mean by public health value is, say you have a product which is killing mosquito, but that doesn't mean it has an impact on the disease. So what WHO wants is evidence that this new product reduces the disease. It of course reduces the mosquito, but at the same time has impact on our health. And that is what evaluation of public health value is. And then it advises WHO whether public health value can be demonstrated in this intervention by carrying out studies in different settings. Now, there are several new tools in the pipeline. So for malaria, for example, there is spatial repellents, endectocides, Eve tubes, full house screening, topical repellents, bait stations, etc. We are focusing on dengue. So for dengue, we really have reduction of pathogen transmission induced by Wolbchia. We have spatial repellents. We have auto dissemination devices, sterile insect technique, and also topical repellents. These are the new tools currently undergoing trials in several parts of the world. So just to review, what do we have for dengue vector control? First of all, we know that in the 1960s, by targeted indoor spraying in South America, and due to the fear of yellow fever, they managed to eliminate Aedes between 1950s, 60s, and early 70s. So Aedes mosquito was almost wiped out from South America, and this clearly showed that targeted indoor residual spraying has an impact. But unfortunately, today we need more evidence base. And so there is a study going on, basically, which is a case control observation study. This has been published, but actually the same group is carrying out a randomized control study in Mexico to prove the public health value of this intervention. So targeted residual spray has potential, but we need more evidence to give recommendations on it. The second is the lethal OV trap. Now there are several traps available, and these traps many of them are already in the market. but these traps are trying to generate data to show that they have public health value. So there is CDC trap. There are several publications which are showing some level of evidence, but the evidence is rather low. Then we have outdoor residual spray. This is a perifocal spraying, which was done mainly for yellow fever campaign, but again, we need more evidence now. Indoor space spraying, basically space spraying used very often in dengue control, frankly, the indoor residual space spraying has some impact, and we have some evidence on it, but outdoor space spraying, we really do not have much impact on the disease transmission. There are, of course, other studies like treated window screens, insecticide-treated curtains, and outdoor space spraying. There are studies ongoing, but we still need more epidemiological evidence. So one important new intervention in dengue vector control is spatial repellent. Now, spatial repellent is basically a sort of pad, which is basically transfluthrin-based emanator. It can be in different ways. The way they design it will depend on the final product. But there are epidemiological trial in progress. One in Indonesia for malaria. They are completed, but it was not very successful. So they are carrying out 2 other studies for malaria. But for dengue, they have done a study in Peru, which shows an impact. And they are going to do a second study in Sri Lanka, and hopefully we will get more data. So spatial repellent is definitely one of those interventions which is now showing some level of evidence, and we hope we will get more evidence base to really prove its public health value. The other one, which is in the front runner, is Wolbchia. And I know in Yogyakarta, they have done a randomized control trial, which has shown a very good decline in dengue prevalence by around 77%. And so this Wolbchia is basically a replacement method, which means that by releasing mosquitoes, which has Wolbchia in their body, we are able to promote that group of mosquitoes and make sure that the wild population is slowly replaced by Wolbchia infected Aedes mosquito. Now, what does Wolbchia do? So basically, Wolbchia is able to arrest the transmission of the virus within the body of the mosquito. It also reduces the mosquito's lifespan a little. And so, in other words, it has definitely been able to prove that this can control. By replacing Aedes population with Wolbchia infected Aedes population, we can control dengue transmission. So there is a study, and what Vector Control Advisory Group did was they have been constantly advising the group, and Vector Control Advisory Group has agreed that this has public health value. Now, once this is being done, we are moving. So basically, we have spatial repellent, we have vector traps, we have Wolbchia here, which is proven to have public health value. Then the fourth one, which I want to briefly mention, is the sterile insect technique. Now, sterile insect technique is promoted by the International Atomic Energy Agency and other groups, where we are radiating mosquitoes, mainly the males, releasing them into the field, and this leads to population decline. So this technique, of course, they have not proven the public health value yet. They have proven that mosquito population can be reduced, but we still need epidemiological evidence. So the Wolbchia part is the one which is still the most promising front runner as a new tool for dengue control. Now, in WHO, we also developed in parallel what is called a guideline for this. And all guidelines are very strictly done. So there is we set up a steering committee. We have a guideline development group, which are all groups of experts with absolutely taken on based on their independent skill and who has no conflict of interest. So these groups of experts really advise WHO to formulate questions and to make sure that the evidence generated is properly graded. So we carry out a systematic review, and we also grade these evidence. Now, Wolbchia is basically right now in step 5 in WHO process. We still need the final clearance from the guideline development group. And we also have an internal guideline review committee, which does the final clearance, because WHO is very strict with any recommendation, because it has got bearing in countries, and countries can say that what we did was wrong. So we don't want that to happen. We go very cautiously, and these recommendations are based on thorough review by renowned experts. So basically, this is where we are. And to really conclude, for dengue vector control, we still need to rely on locally adapted vector control to fight dengue. And one of the reasons why dengue is struggling for vector control is because we do not have a sustainable tool which we can use year after year. So we hope Wolbchia would be one. So we also need to know the vector and its ecology, because these vectors, mainly the Aedes mosquito, they breed in different habitats. We also need to know their insecticide susceptibility. Target indoor residual spraying has some potential. Just adult control is not enough. The adult control has to go hand in hand with larval control for dengue. And the future of our control program depends on combination of new tools and strategies which are coming. So I think with that, I conclude my presentation, and thank you very much for this opportunity.
Thanks, Raman, and really an important insight into WHO's processes for reviewing the evidence base for new tools. And obviously we're very interested in seeing the Wolbchia introgression replacement method, if you like, receive that WHO endorsement and find a pathway in countries that are yet to trial this method for dengue control. And clearly, the evidence in Yogyakarta is incredibly compelling of its impact, really real-world evidence of its impact at scale. So without further ado, pleasure to introduce Henrik Salje. Henrik is currently a lecturer at Cambridge University, and before that, Institut Pasteur in Paris. By training, he's really a mathematician, I think, at heart, and with a biostatistics background at Hopkins in the Department of Epidemiology, and then some time with Derek Cummings in Florida before starting his own group, Institut Pasteur, and in the last 2 years moving across to Cambridge University. And Henrik works on arboviruses with a focus particularly in Asia, and brings his mathematical modelling expertise to important questions of transmission. And today, how Henrik can approach measuring the impact of Wolbchia in particular dengue endemic settings, with Rio de Janeiro as the case study today. If we could roll to Henrik's talk, thanks.
So hello everyone. Thank you very much to the organisers for giving me the opportunity to present some of work on modelling, both from my group and others, in trying to understand the effect of Wolbchia to combat dengue. I'm a professor at the University of Cambridge, where my group, the Pathogen Group, works on trying to understand the emergent spread maintenance and options for control of different infectious diseases. So, as I'm sure you'll have seen in this session, dengue is this really endemic problem in large parts of the world. You have this constant, non-stop transmission in many places. This is here, the map is this sort of an estimate by Battenall from 2012, giving an idea of where we expect dengue is regularly circulating. And I pulled out one time series here from Bangkok, from a single Bangkok hospital, showing that over 30 years, you just have this ups and downs in dengue transmission. If we would drill down the location of cases here on the left-hand side and colored dots in where people live by the serotype that infected them, we really see that is a problem sort of throughout cities where you have this co-circulation of many serotypes. Certainly true for large crowds in Asia. And well, today we've really been heavily reliant on trying to kill the mosquito, both by looking for over-positioning sites and get rid of those, or through these very public, often actions of fogging, insecticide spraying. However, we really don't have a good evidence base as to whether these huge and expensive efforts, billions are spent each year on them, are actually any good at reducing dengue. And part of the problem is that this property of dengue transmission, that is highly variable in both space and time, means that when you see ups and downs, it's difficult to really attribute them to these focal intervention measures. The new technology which has come around in the last decade or so is through Wolbchia. So Wolbchia is a bacterium that's found in many insects, but not normally in Aedes aegypti, the main vector for dengue. And Wolbchia is interesting for two reasons. First of all, when you do put Wolbchia into aegypti, it is dramatically less good at being able to transmit dengue, as well as it seems other arboviruses. On top of that, Wolbchia induces something called cytoplasmic incompatibility. What this means is when uninfected females mate with infected males, the offspring die off shortly after fertilization. By contrast, infected females can mate with both uninfected and infected males, and the resulting progeny will have Wolbchia. And that's very interesting because it means you can release females, infected females, into wild-type populations. And bit by bit, they should take over, Wolbchia should take over the wild-type population as well, as it's illustrated in this bottom panel here. Some early mathematical modeling work has sort of identified, well, actually, this doesn't happen straight away. In fact, what you need to do is to identify a threshold. And once you reach this threshold, then Wolbchia should take over the population. This work from the 1990s by Michael Torelli showed that, in fact, the threshold seems to depend on the trade-off between its benefits of cytoplasmic compatibility and the fitness costs of Wolbchia carriage, particularly through reduced lifespan. Now, exactly where this threshold is remains to be completely determined. These initial estimates of just around 0.2 are probably a bit low. Now, the potential Wolbchia has been shown in randomized controlled trials. The first one was the results of which were released recently from Yogyakarta in Indonesia. And this was a very nice study design where they essentially divided up the city into different patches and released Wolbchia in some and not into others. And what you saw is over this 1 year release period, there was a gradual increase in the proportion of Aedes aegypti that were infected with WML, so this strain of Wolbchia, and then post-releases, it stayed in there, which is fantastic to see, which sort of highlights how this theoretical self-sustaining mechanism of Wolbchia seems to be played out in this setting at least. In the control areas, there did seem to be some bleeding of Wolbchia. What I mean by that is if you look at these different control areas, after a period of time, you did start seeing Wolbchia in these areas too. So this shows that Wolbchia can take over mosquito populations in real life. Very importantly too, in fact, it seems to also have a massive impact on dengue. So looking at the spatial distribution of dengue cases throughout this time period, the authors were able to estimate the efficacy of this intervention on dengue incidence as well. So it's not just the Wolbchia taking over the wild population. In fact, it was able to reduce dengue incidence by an estimate of close to 80%. which is really tremendous. And actually, the true numbers likely to be greater than this. So nice work by Suzanne Dufault started looking at the serotype distribution of the cases and started comparing the tendency for cases to be of the same serotype within small spatial distances. And what we would generally expect is that if you take a case of dengue and you look in the case homes around that initial case, they will generally be of the same serotype, because I might be infected by dengue 1, and infect somebody, and generally we know that dengue transmission is really quite focal. And so people around me would also be infected with dengue 1. And indeed, in the control area, that's exactly what we found. So there's a 5-time increase odds of cases being homotypic or at distances of 50 meters. However, in the good treated areas, in fact, you didn't see any spatial dependence of cases. So what that means in the serotypes of cases, and what that means is in the cases you are seeing in the treated areas are probably getting their infections elsewhere. Now, once we have an idea of the effectiveness of this technology, we can then start trying to estimate the impact. This is some nice work at a London school, which took Indonesia a whole and said, well, okay, let's release, pretend we release Wolbchia everywhere. What is the potential efficacy of this? And ultimately the number of cases we would avert, and saying in the large population centers, you'd be looking at tens of thousands of cases averted each year of dengue, which is super exciting if we think about these very sticky endemic distributions of dengue I showed. Ultimately, the number of cases we would avert, and saying in the large population centers, you'd be looking at tens of thousands of cases averted each year of dengue, which is super exciting if we think about these very sticky endemic distributions of dengue I showed at the beginning of my talk. This is a real opportunity to disrupt that substantially, which we haven't been able to do so far. Some of the
reproduction of the insects it lives in to give itself an advantage. It works like this. If a male insect has Wolbchia and mates with a female that doesn't, then the eggs she won't hatch. If the female has Wolbchia and the male doesn't, she would lay her normal number of eggs. They would all hatch and all offspring will carry Wolbchia. When two insects that both carry Wolbchia mate, the eggs will hatch and all offspring will carry Wolbchia. Until nearly all the insects within a population have the bacteria. We wanted to see if we could use Wolbchia as a way to stop dengue transmission.
Treated areas are probably getting their infections elsewhere. Now, once we have an idea of the effectiveness of this technology, we can then start trying to estimate the impact. This is some nice work at a London school, which took Indonesia a whole and said, well, okay, let's release, pretend we release Wolbchia everywhere. What is the potential efficacy of this? And ultimately the number of cases we would avert, and saying in the large population centers, you'd be looking at tens of thousands of cases averted each year of dengue, which is super exciting if we think about these very sticky endemic distributions of dengue I showed at the beginning of my talk. This is a real opportunity to disrupt that substantially, which we haven't been able to do so far. Some of the work that we've been doing is in different locations in Rio de Janeiro in Brazil. Now, this is a place that has enormous amount of dengue and also enormous amount of chikungunya. And we were able to tap into the city health department, which does something really fantastic, which is the systematic geocoding of cases that turn up in any hospital in the city. And what they see is something like nearly 30,000 dengue cases on average each year. That's something like 15,000 cases of chikungunya since it was first emerging in 2016, and really throughout the city. In 2017, the World Mosquito Program started a release program in the city, in this northeast area of the city, broken up into different release centers. And it really was this phenomenal effort where they released something like close to 70 million mosquitoes across nearly 30,000 locations in this part of the city over a 2-year period. And the output of that isn't as beautiful as what we saw in Jakarta, in that in some places, some of these outlying areas, you did see, this is here on the x-axis, the time of release, and these are different 500 man-meters by 500 meter spatial units, and it's colored in by the proportion of trapped mosquitoes in that space-time unit that are infected with WML. And whereas darker green means that you have a higher level of integration. And so what we saw in these outlying regions is you did see more and more dark green. But actually that picture was not true everywhere at all. And even these outlying areas, it seemed to go up and down. And in fact, if we look at the overall picture, this here on the x-axis is the time to its initial release. In black here is a number of mosquitoes released per month, which released, which reached up to 4.5 million in any month. And here on the left, and the axis for this red, which is actually just the average WML percentage in the trapped mosquitoes following release. And whereas in Indonesia, you saw this beautiful increase up to 100% quickly, that's not at all what we see overall in Rio. And in fact, the mean over this 2-year period, Wolbchia was around 34%, despite the huge numbers of releases. And when we drill down a little bit into why that might be, we notice that actually if you compare the dengue incidence in time periods prior to the release with the Wolbchia percentage you see in those locations, we see that Wolbchia was far more successful in places that historically didn't see that as much dengue, and in fact was less successful in places that historically did see more dengue. So in dashed lines here, you have the years prior to the releases, and the red is the post the release. And as these are all generally higher than 1, it's saying, okay, well, generally these places which had subsequently had low WML, which historically had a lot of dengue. And this may point to places which just have a lot of dengue, having a lot of mosquitoes, and the releases maybe just weren't able to successfully penetrate and introgress in these areas. On top of that, we see a temporal effect. Now, both dengue and chikungunya are highly seasonal in Rio, with peaks in transmission very consistently in their summers, around the months, especially March, April, May. This is a time period where mosquito levels are greater. So both Aedes aegypti are highest during this period, and Aedes albopictus, which are found at lower levels throughout Rio too. But when you look at introgression levels, this is actually, we saw a strong dip in introgression levels during this summer period. And here I've just plotted as well the temperature profile, showing that this is when temperature tend to be a bit greater. Now, this observation is supported by laboratory experiments, which shows that once you ramp up the temperature a bit, the fitness cost increases, and the probability of introgression does go down. Now, this, if we think about the growing and ever-growing problem of climate change, this suggests that this strain of Wolbchia WML may encounter problems, introgression, especially in warmer climates, and in coming years as places get warmer and warmer. Now, so what I presented here is a different environment. This is not part of a randomized controlled trial. We don't have the benefits of being able to compare areas where you did have releases with comparable areas where you didn't have releases, just simply compare incidents. We also didn't have this beautiful increase in introgression level. We're kind of stuck in the middle, this intermediate levels, and we go up and down, up and down. And so it's not evident just by looking at the number of infections whether or not WML was still having an effect ultimately on both dengue and chikungunya transmission. What we can do in this context is try and build mathematical models and incorporate this complexity. So I'm not going to go too details into the actual equations, but to say that you can think about modeling the number of dengue cases or number of chikungunya cases within each cell, at 500 meter per cell in a particular month. And we can say, well, actually, the number of cases we observe is going to depend on the underlying population size, the number of people who live in that location, as well as the things we are interested in. So the level of WML in that place, in that time. But also we need to think about, well, actually, does seem to be this underlying difference in the number of dengue cases in a particular area. Some areas just do seem to have every year high levels of incidence, some places have lower levels of incidence. On top of that, there's a strong seasonal component. So you have both within a year, there are high months and low months, and year on year, there seem to be places, there seems to be peaks and higher years and years where you have smaller epidemics. By incorporating all these things together, and you have to incorporate all these together, we can actually then start really identifying what is this role of the WML level in any month on the number of cases you observe. And the results are like this. So here we have on the x-axis the level of WML within any location in any month. And the y-axis is an estimate of the incidence risk ratio, both for dengue in yellow and chikungunya in blue. And what we see is a very interesting dose response. So here, this is the level of WML that we saw. And with dengue, you see that both dengue and chikungunya, as you have more and more WML, we do see a reduced incidence of both dengue and chikungunya. Interestingly, with dengue, this level does approach the estimated effectiveness that we observe in a randomized controlled trial, suggesting that if we are able to get this self-sufficient above this threshold, so suddenly WML is stably integrated into the mosquito population, then we should be seeing similar levels of effectiveness. Chikungunya doesn't seem to reach those levels. We don't know exactly why. There is certainly albopictus in this community, which may be able to maintain another level of transmission. It certainly remains an open question. I'm just going to finish off with some conclusions about the roles of models, and in being able to tease apart the effects of interventions, which are often spatially focused and also temporally focused. And whilst I've applied it here for Wolbchia, I would say that these kinds of approaches would work with trying to provide an evidence base for the role of your traditional insecticide spraying. A big problem that we have seen is there doesn't seem to be very good data sets which are carefully collected where spraying activities occur, where and when spraying activities occur, as well as very good data on where and when cases occur. These kinds of data sets are really what we need to be able to employ such kind of methods to really understand what actually is the benefit of these large spraying activities. This underlying heterogeneity in where cases are occurred does complicate understanding the impact of spatial-time interventions, especially outside randomized controlled trials. But these models can get over these problems as long as you have good data. And here, working with the City Health Department, which have been doing this fantastic geocoding exercise, has really allowed us to do this. Thinking more specifically about Wolbchia and Rio, it does seem the integration has been hard in it, despite the large number of releases. The reasons are unclear, but it is a very complex terrain, both physical geography, in terms of the rapid elevation changes, big roads and so on, and social, a lot of favela communities here, especially in the project area, which it is difficult to understand exactly what leads to slower level of integration. It does appear to be a role for temperature. And maybe thinking about warming climate, there might be a need for next generation of Wolbchia strains to counter this. Nevertheless, even with intermediate levels of integration, we do seem to have an opportunity to reduce the incidence of dengue and chikungunya. Just finish off by acknowledging, especially the work here from Rio, led by my PhD student Gabriel Santos, as well as the partners of the Mosquito program in Rio, who really have led this fantastic, enormous effort to release such a high number of mosquitoes. And finally, the City Health Department, who do the systematic geocoding cases. Thank you very much.
So thank you to our three speakers. Love to do it in person, but a remote thank you. I hope you all enjoyed those presentations. I thought they were all excellent, all timely, and all relevant, certainly, to the wider discussion today on applying Wolbchia and what we've learned, particularly from Jakarta. So I will hand back to the organisers. Thanks.